In this video, we are going to see the polarization topic. So polarization is defined with respect to electric field. Even though it is the property of the electromagnetic wave, we need to define the polarization with respect to electric field. Okay. Then what is polarization? So polarization is actually the locus of tip of electric field as a function of time at a fixed location. Generally, we will consider electromagnetic wave is traveling in the z direction. Okay, so this is the direction of propagation. So if you take the electric field is like this, and magnetic field is like this, and the wave is traveling in the z direction. Okay, so magnetic field is oriented in y direction. Actually, here I have taken the orientation of the magnetic field is in the y direction, and the orientation of electric field is in the x direction. So what we need here, the locus of the tip of the electric field, okay, as a function of the time. So you need to change the time, but you need to fix a z value. That means at fixed location in the space, by changing the time, how the electric field is varying, that locus we have to take. For example, if you change the time, this is the electric field representation. If you take the trace of all these peaks of the electric field with respect to time, then you will get a horizontal line. Okay. Or if the electric field is rotating like this, as time is changing, the electric field is rotating like this. Then you may see the circular shape. The locus, if you take, you may get the circular shape. In some other cases, the electric field variation is like this. As time is changing, the strength of the electric field is increasing in the form of the line, and then it is reversed and it is coming like this. That means you are observing a straight line. Okay, so in some other cases you may observe the elliptical shape. Ellipse can be like this, ellipse can be like this, ellipse can be like this also. So what we are observing here, this locus, whatever the locus we are telling, that locus can be a straight line, that locus can be a circle, that locus can be a ellipse. And here so many types are there. What are those types means? Straight line means the line can be like y is equal to mx with positive slope, and with the slope is 0, that means horizontal line. Slope is infinity, that means vertical line, and slope can be negative also, like this. Okay, so all these things are coming under straight line only. That means this type of polarization is said to be linear polarization. So in case of the linear polarization, we have different types. Okay, that is a horizontal polarization like this, vertical polarization like this, and simply linear polarization with slope 1 or positive slope, and here slope is negative. So all these things will come under linear polarization. Now coming to circular polarization. Okay, if the locus is circle, then we can able to call that is a circular polarization. That particular electromagnetic wave is consisting of circular polarization. But very simple thing here, one thing you need to understand, in the circular polarization also we have two types. One is right hand, second one is left hand. Okay, RHCP, right-handed circular polarization and left-handed circular polarization. Okay, so why we have two types in the circular polarization means, so straight line means we can draw like this, we can draw like this, we can draw like this, we can draw like this. But what about circle? Circle means it will be like this only. Okay, but here I will tell one thing, that is circle you can draw like this by extending the curve like this, you can draw like this. This is the circle, the way of drawing a circle. Otherwise, you can draw the circle like this also. Okay, this is also circle. So the way how this circular polarization is created, that based upon that way, we have divided this into two types. One is RHCP, second one is LHCP. And out of these two, which is RHCP, which is LHCP, that we will see, okay, in coming few minutes. Okay. Similarly, in case of elliptical polarization, you may have ellipse like this or ellipse like this. That means the major axis is oriented in some direction. But here major axis is horizontally oriented. Or the tilted ellipse is also available like this. Or you may have like this. So in the ellipses are also we have so many types, and each type can be divided into the right-handed elliptical polarization, that means RHEP, and left-handed elliptical polarization, that is LHEP. So like this, so many types are there. Anyhow, we need to change the time at fixed location to get the locus of the electric field. That particular locus is called polarization of the electromagnetic wave. Okay. Now, mathematically, we are going to see how this particular polarization will be defined. So as I said, the electric field is traveling in the z direction as a function of time. That means it is changing with respect to space variable z and time variable t. And we'll assume that this particular electric field is having the two components. One is x component and second one is y component. Both components are available. And x component I am taking like this, that is E1 cos omega t minus beta z x cap. This entire thing is simply Ex. Okay. And then E2 cos of omega t minus beta z plus phi. What is this phi? I will tell. Phi is the phase difference in between this x component and y component. Okay. So, as per the definition of the polarization, it has to be considered at a fixed location, and for simplicity we can take that location is equal to 0. Then E of 0 comma t is equal to, you will get E1 cos omega t x cap plus E2 cos omega t plus phi. By taking z is equal to 0, you can get an electric field expression like this. Okay. And as I said, this E1 cos omega t is representing the x component of the total electric field, and this E2 cos of omega t plus phi is representing the y component of the total electric field. Okay. So from this x component, we can write Ex by E1 is equal to cos omega t. Now itself I am writing sin omega t. It will be helpful later. That's why I am writing now. Cos omega t is Ex by E1. So sin omega naught t is nothing but square root of 1 minus cos square omega t. So it will become square root of 1 minus Ex by E1 square. Okay, so wherever cos omega t is there, you can replace with Ex by E1. Wherever sin omega t is there, you can replace with the square root of 1 minus Ex by E1 square. Now you write expression for Ey. So Ey, what did we get? E2 cos of omega t plus phi. and send that E2 to the left side, then you will get Ey by E2 is equal to cos of omega t plus phi. You can expand this one by using the formula cos A plus B, that is cos A into cos B minus sin A sin B. Like this I have expanded this one using cos A plus B formula, that is cos A cos B minus sin A sin B. But already you know what is cos omega t and you know what is sin omega t. Just to substitute this cos omega t and sin omega t. So what we will get? Ey by E2 I am writing from left side. So Ey by E2 is equal to cos is nothing but what? Ex by E1 cos phi minus sin omega t is nothing but square root of 1 minus Ex by E1 square. This is simply sin omega t and this is multiplied with sin phi. Now write equation for only this square root of 1 minus Ex by E1 square sin phi. Okay, and square that one. Then what you will get? 1 minus Ex by E1 square, and here sin is also squared, so that you will get here sin square phi, and if you multiply this one with 1 you will get here sin square phi here also. Okay, 1 is multiplied with this one and it is equal to, you will get Ex by E1 square cos square phi plus Ey by E2 square minus 2 times of Ex Ey by E1 E2 cos phi. So don't confuse here. I have made this, I sent for example this one square root of 1 minus Ex by E1 square sin phi to the left side, and I brought this Ey by E2 to the right side. So I squared on both sides. Then left side we got this one, and right side we have applied A minus B square. So A square plus B square minus 2AB, like this we got. Okay. Now what we can do? We can able to write this entire thing here. Ex by E1 square sin square phi is there. Here Ex by E1 square cos square phi is there. So if you send this one to right side, and we can take Ex by E1 square as common, then you will be left with cos square phi plus sin square phi, and we know cos square phi plus sin square phi is 1. And then what are the remaining terms? Ey by E2 square minus 2 times of Ex Ey cos phi by E1 E2 is equal to sin square phi. Then final equation will be Ex by E1 square plus Ey by E2 square minus 2 times of Ex Ey cos phi by E1 E2 is equal to sin square phi. So this is the equation required to be remembered. And from this equation only we are going to get several conclusions or types of the polarization we will get. Okay. So again I am writing that same equation, Ex by E1 square plus Ey by E2 square minus 2 Ex Ey cos phi by E1 E2 is equal to sin square phi. Okay, so this is a general elliptical polarization. It is general elliptical equation, so that it is a general elliptical polarization. That is nothing but by default the signal will be having elliptical polarization. Whatever we are going to see different cases, all those are sub cases of this particular elliptical polarization only. For example, ellipse is like this. This is the major axis. This is minor axis. If you make this minor axis length is equal to 0, then if you reduce, first of all, this will become like this. This will become like this. If you make that minor axis length is equal to 0, it will become one vertical line. So this linear polarization, this vertical polarization or the linear polarization can be obtained from the elliptical polarization by making minor axis is equal to 0. For example, your elliptical polarization is like this, and this is the major axis, this is the minor axis. If you take here also minor axis length is 0, you will get the line like this. That means a linear polarization you will get. If your elliptical polarization is like this, and if you make the minor axis length is equal to 0, then you will get linear polarization like this. Next one is, if you have the control on the this particular minor axis length or the major axis length, if you make both major axis length and minor axis length both are equal, then surely you will get a circle. That means circular polarization. So linear polarization, that means a straight line, locus is straight line, and circular polarization, that means a locus is a circle. These two are the subcases of the elliptical polarization only. Okay, so this is what you need to remember. Now we'll see different cases. So case 1, simply you have to take phi is equal to 0. What will happen? You see how this particular equation will be changed. So ex by e1 square plus ey by e2 square, phi is equal to 0. Here cos 0 is nothing but 1, but here sin 0 is nothing but 0. So right side anyway you will get 0, and left side you will be left with 2 ex by ey by e1 e2. Cos phi means 1. This is equal to 0. Now exactly it is in the form of a minus b, a square plus b square minus 2ab. That means a minus b square is equal to 0. So ex by ey minus ey by e2 square is equal to 0. And this can be rewritten as ey is equal to e2 by e1 into ex. Like this we can write. So this is exactly looking like y is equal to mx with the m, that means slope is equal to e2 by e1. So on the x-axis if you take ex component, on y-axis if you take ey component, then you will get a straight line. Okay, what is the locus here? You will get a straight line with a slope e2 by e1. So this ratio e2 by e1 is deciding the slope. That means here some cases we can able to get. If you have e1 is equal to 0, then slope m is equal to e2 by e1 is equal to infinity. That means vertical line. Okay, so you will get the electric field orientation is like this. Vertical line you will get. Linear polarization, in that vertical line you will get. Okay, that is what is the meaning of this one. E1 is equal to 0 means x component is equal to 0. Only you have y component. That is the meaning of this one. Out of two components of the electric field, whatever we have considered x component and y component, you will be left with only y component because we have made E1 is equal to 0. That means E2 cos omega t minus beta z plus phi cap. Only this part is available. Since it is oriented in the y direction, we have the vertical polarization only. Instead of this one, if you take E2 is equal to 0, that means slope is equal to E2 by E1. So you will be left with the slope is equal to 0. That means horizontal line. Okay, that means you will get like this. The polarization will be like this. As time is changing, the locus of the tip of the electric field will be changing like this. If you take the trace, you will be getting one horizontal line. What is the meaning of this one? E2 is equal to 0 means y component is 0. So here you will be left with only one component, that is x component. That means E1 cos omega t minus beta z into x cap. Now both are not equal to zeros. That means slope is equal to E2 by E1 is available. Certain slope is there. But here also we have two cases. For the time being, you assume that it is positive slope only. Okay. But it may be, in this case, E2 may be greater than E1 and E2 is less than E1. If it is greater than E1, slope is greater than 1, you will get. E2 by E1 value is greater than 1. E2 by E1 is greater than 1. And in this case, in the second case, you will be having less than 1. That means how you will get the slope here? This line is representing slope is equal to 1. These lines are representing slope is less than 1. And this line is representing slope is greater than 1. So like this you will get the linear polarization. Okay. And one more thing is also there. It is not enough. We have this entire thing is possible when you take phi is equal to 0. Okay. This is important here. So simply we can tell now linear polarization is obtained, or vertical polarization, horizontal polarization is obtained when you take phi is equal to 0. But when you take phi is equal to 180, what will happen? So once again I am taking the original equation, Ey by E2 square plus Ex by E1 square minus 2Ex Ey cos phi by E1 E2, that is equal to sin square phi. Now if you take phi is equal to 180, then what you will get? Here cos 180 is minus 1. Here already minus is there, so minus into minus is plus. Sin 180 is 0. So it is also similar to the previous one, but here you will get a plus b square. So final equation will be like this. Ey is equal to minus E2 by E1 you will get. Okay, into Ex. That means slope is negative. Slope is negative means all the previous cases will be available with the negative slope. With the negative slope means in the second and fourth quadrants the line will be available. So anyhow, to have linear polarization, the conditions are given with respect to phase difference in between x component and y component, that is phase phi is equal to 0 degrees or phase phi is equal to 180 degrees. We did not comment on E1 and E2. These two can be equal, cannot be equal also. There is no condition with respect to amplitudes of the x component and y components, but there is a condition with respect to phase difference, that is 0 or 180. If you take 0, positive slopes you will get. If you take 180, negative slopes you will get. This is about complete idea regarding the linear polarization. Now case 2 we'll see. Case 2, that is circular polarization we'll see. Circular polarization. So circular polarization can be obtained by meeting this particular condition exactly. That is E1 is equal to E2 and phase difference is equal to plus or minus 90 degrees. If you take plus 90, you will get left-handed circular polarization. If you take minus 90, right-handed circular polarization. But with plus 90, you may get right-handed circular polarization also. With minus 90, you may get left-handed circular polarization also. Don't confuse here. I will tell when you will get all these things. This is possible when the wave is traveling, wave motion is in positive z direction. And this is possible when wave motion is in negative z direction. Okay. So in order to avoid the confusion, now you keep this negative z direction aside. Don't think about this one. You assume wave is traveling in the positive z direction, and if the phase difference between x component and y component is plus 90, that having this left-handed circular polarization LHCP. And if the phase difference is minus 90 degrees, then that is right-handed circular polarization. Actually, it is opposite to this one. Okay. Anyhow, here there is a condition on the amplitudes also. There is no condition regarding amplitudes in case of the linear polarization. The both amplitudes can be equal, cannot be equal. There is no criteria regarding the linear polarization. But for the circular polarization, surely the amplitudes must be equal and phase difference should be either plus 90 or minus 90. Okay. So if you apply all these things in the basic equation, general elliptical equation, and here for explaining purpose I am taking this is equation 1. So if you assume E1 is equal to E2 is equal to E naught and phase difference is equal to 90 degrees. Substitute all these things in equation 1, what will happen you see. Ey square plus Ex square cos 90 is 0, that means the third term will not be available. Sin 90 is 1. So 1 into E naught square will be E naught square. Now this is exactly circle equation with coordinates Ex and Ey and with radius E naught. Here radius E naught, r is in 0 comma 0 and coordinates are Ex and Ey. So if you take on x-axis Ex component, on y-axis Ey component, by changing the time, you will get the trace will be simply circle. Ex square plus Ey square. That means like it is like x square plus y square is equal to r square. Okay. So you will get the circle like this. And because we have taken plus 90, you will get left-handed circular polarization. That means the electric field trace will be like this. Okay. Vector, vector, vector. As time is changing, the electric field vector is rotating like this. How to remember this one? Okay, how to remember in the sense, you see, actually it is traveling in the clockwise direction. Some people will remember like this also. Clockwise is nothing but left-handed circle polarization. But we can't able to remember like this also sometimes. So how to remember this one exactly? What is the meaning of introducing the terms left-handed? Left-handed. Why it is taken like that? Now see carefully. When you take this clockwise direction with your left hand, you can able to mention this orientation of this particular clockwise representation. That means electric fields are moving in the clockwise. Okay, electric field vector is making the circle representation by rotating in the clockwise direction. So you can keep your left hand in this particular direction only by mentioning your thumb, left hand thumb in the positive z direction. Okay, your left hand thumb is there in the positive z direction and your left hand curl. Okay, whatever the four fingers are there, those four fingers you can able to bend in such a way that is oriented in the clockwise direction only. Okay, so your fingers will be like this. Your hand fingers will be like this. Okay, assume this is the hand, you have hold it like this and here thumb is there. You need to mention your thumb in the positive z direction. It is coming out of the board. Okay, I did not draw properly here. You can able to assume like that. Okay, this is about phi is equal to plus 90. That means left-handed circumpolarization will get. If you take if you take phi is minus 90 and wave is coming in the or traveling in the z direction only, plus z direction only, then you will be having the right-handed circular polarization where the circle will be formed like this. That means the electric field is rotating in the anti-clockwise direction. Anti-clockwise direction. Okay. Polarization, that is case 3. Okay. As I said, it is a general polarization. That means if linear polarization is not available or circular polarization is not available, then wave contains surely elliptical polarization. That means if phi is equal to 0, that is linear. If phi is equal to 180, that is linear. So in case of elliptical polarization, we should not take phi is equal to 0. We should not take phi is equal to 180. Okay, you have to remember like this. Carefully you have to remember. If you take phi is 0, surely that is LP. If phi is 180, surely that is also LP with negative slope. So in case of elliptical polarization, you should not take those two conditions. And in case of CP, we have conditions like this. E1 is equal to E2 and phi is equal to plus 90 or minus 90. So you should not take like this. That means you should not take E1 is equal to E2. At the same time, you should not take phi is equal to 90 or phi is equal to minus 90. So you cancel this one, you cancel this one, you cancel this one. Or if you take like this, E1 is equal to E2 and phi is not equal to 0, phi is not equal to plus or minus 90. Now E1 is not equal to 0, sorry, phi is not equal to 0, phi is not equal to 180. That means you are cancelling the linear, but you have made, you are not taking phi is plus 90 or minus 90. That means you are cancelling CP also. With this one you can tell LP will not be happening. With this one you can tell CP will not be happening. So you can have E1 is equal to E2. This condition is okay. But you are not having phi is not equal to 90 or phi is not equal to minus 90. So that surely you will not get CP also. Okay. So you will get in this condition EP. Now you take different values of E1 and E2 and phi is not equal to 0, phi is not equal to 180. This is for cancelling the LP. And already CP also cancelled. Since we have taken E1 is not equal to E2, CP also cancelled. So now you take phase is equal to 90. So you should get EP only. Or phase is equal to minus 90, you will get EP only. So EP can be obtained like this. So I am giving the numbering here 1, 2. So first type of elliptical polarization, how it will be available. Second kind of polarization, how it will be available. Since we have plus 90, plus 90 minus 90 is related to LHEP or HEP. So I will talk with respect to plus 90. Okay, left-handed elliptical polarization. So since we don't have the equal values for E1 and E2, you will be having the elliptical polarization will be oriented along the y-axis, or elliptical polarization, this ellipse major axis will be oriented on the x-axis. Okay, this is for case 2. Here already I have mentioned. But when you will get this first one means E2 is greater than E1. And second one is for opposite case, E2 is less than E1. What about case 1? In case 1, we have made E1 is equal to E2, but phase difference is not 0, not 180, not plus or minus 90. So you will get the tilted ellipse. The tilted ellipse you will get. Okay. So in this way we have different types of the elliptical polarization. So here summary I will write. So see carefully. So we are working with E1, E2 and phase difference. Okay. Actually E1 and E2 not values, ratio we have considered. E1 by E2 ratio and phi. Based upon these two values only we got different polarizations. So now for example electromagnetic wave is with phi is equal to 0. Okay. When you take phi is equal to 0, you may have E1 and E2 same, E2 greater than E1, E2 less than E1. So here E2 by E1 is actually 1. Here E2 by E1 greater than 1. Here E2 by E1 less than 1. Whatever it may be, since phi is equal to 0, you will get linear polarization. But since E2 by E1 is equal to 1, you will get the trace will be like this. Here the trace will be like this. Linear line passing through the origin with slope is 1. Slope is greater than 1. That means a very large value you can take nearer to this. It is oriented towards the y-axis. Slope is less than 1 means the line is oriented towards x-axis. And similar kind of things you will get. That means this is LP. And similar kind of things you will get when you take phi is equal to 180 also. Okay. So phi is equal to 180. Same thing you have to take. That means here also we have 3 cases. E1 is equal to E2. E2 is greater than 1. E2 less than E1. So here E2 by E1 is 1. E2 by E1 is greater than 1. E2 by E1 less than 1. But actually here we have to work with the negative slope. So in the first case we will get the curve in the or that locus will be in the second and fourth quadrant. Next one is also in the second and fourth quadrant only, but oriented towards the y-axis. Second and fourth quadrant oriented in the x-axis, because we will be having the negative slopes. Negative slope, positive slope, it is also LP. Okay, simply with the angle, whenever angle is equal to 0 or 180, LP will get. Now we'll see CP. That means E2 is equal to E1 and phi is equal to plus 90. E2 is equal to E1, phi is equal to minus 90. Okay. So when you take like this, what type of polarization you will get? Circular polarization, but EM wave is with these values. EM wave which is traveling in plus z direction. With this assumption only all these things are valid. Okay, if it is traveling in the negative z direction, all these things will be reversed. Okay, so if we continue like this, we'll get here circular polarization, will get, but here it is left-handed CP. That means the circle will be created like this. And here also circular polarization, but right-handed CP, RH CP. Okay. Now we are not meeting these conditions, then elliptical polarization will get. Okay. So you are not taking phi is 0, you are not taking phi is 180, then these two conditions you are not meeting, but you are meeting E1 is equal to E2, but you are not meeting phi is equal to plus, phi is not equal to plus or minus 90. You are taking like this, phi is not equal to plus or minus 90. So because you have taken like this, LP you will not get. Since you are not taking phi is plus or minus 90, CP you will not get. So remaining is elliptical polarization. So based upon E2 and E2 by E1 ratio, you will get this particular ellipse. Tilted ellipse you will get. Okay. Then you are not taking phi 0, you are not taking phi 180, so LP you are not taking. Now you are not taking this E1, E2 equality also. You are taking unequal values of E1 and E2, but you are taking phi is plus 90 or minus 90. So plus 90 minus 90 is actually related to LHEP and RHEP. So how you are getting? This is the tilted ellipse. So when you take E1 and E2 not equal and phi is 90 for example, you may get like this. This one you will get when E2 is greater than E1. And horizontally available ellipse also you will get. This is when E1 is greater than E2. So like this you will get. Okay. So these are the different types of the polarizations we have in case of the electromagnetic wave. Thank you.